Joerg Knollenberg and the MUPUS team, and here is the MUPUS team, and I have to say that I do not have an acknowledgement slide. Oh, okay, oh yeah, okay, that's all right. And I acknowledge to everybody, you know, that everybody already acknowledged. I just follow suit. Okay, let me present the MUPUS first results. MUPUS, first of all, is a novel package of instruments, at least in terms of this thing here. This is a penetrator. It's a nail, so to speak, with a hammer on top, and it was supposed to hammer itself into the ground and measure the temperatures along the rod and the thermal conductivity. It's a sort of a line heat source, heat probe, you know, to measure the thermal conductivity and the temperature sensor. But the package also included temperature sensors on the anchors and accelerometers. So we also do soil science, also by measuring how fast we got into it. And then we have a thermal mapper up here that was looking at the spot where this penetrator is going into, but it was also observing during the descent of the lander towards the comet, and as we flew or hopped or whatever across the surface. So what did we probably do and what did we not do? Actually, unfortunately, we did not penetrate into the ground, and therefore there was no measurement of the near-surface temperature, gradient, and thermal conductivity profiles. But we can use that to put a constraint on the hardness of the soil, so we can use that at least to some extent, although that is an unfortunate failure. Since the anchors were not fired, we did not do the temperature measurement at 1 to 2 meters depth, and also not the accelerometry, on impact of the anchors. What we did do is then we measured the strength of the ground upon the penetration attempt. We did thermal mapping on approach and during hopping across the surface. And we measured the thermal diurnal cycle with both the thermal mapper and with the temperature sensors on the penetrator that was sitting on the ground and trying to get into the surface. Now let me first discuss this penetrometry a little bit. Here is a recording of the depth sensor that the nail is equipped with. And this depth sensor indicates that there was an initial displacement of about 20 millimeters, and thereafter the depth sensor's amplitude was about 5 millimeters maximum. We had envisaged that we did not know what the surface hardness would be, and therefore we have 4 energy levels actually, and we have a software in there that increases if the depth sensor doesn't measure any progress. We increase the power level to the next and the next and the next, and we went up to the full strength on it and hammered for 3.5 hours, but we did not get into the surface. We did not hammer at the full frequency, so we did only every 4th stroke, and we still have to figure out whether we really reached that power level or we are settled on that level here. So that is not fully clear at the moment, and that is important in terms of the constraints on the hardness of the ground. Now we have housekeeping data, for instance, the hammer energy of 1 joule, the velocity of the hammer tip, and so forth and so forth. They put them all together with the observed indentation of the surface of a few millimeters. You can calculate a pressure that we exerted on the surface of about 1 megapascal at least, so that is a lower bound, and because we didn't penetrate, that translates then into a compressive strength or lower bound to the compressive strength of about 1 megapascal. This is something that we had designed the penetrator to of about, because at the time when we designed this experiment, we were all believing that 1 megapascal would not be to be accounted on the surface. However, one should say that a crushing strength of a megapascal for ice is not uncommon. Ice typically has about an order of magnitude more. or maybe even 2, and even snow at low temperatures, has a strength of 10 megapascals or so. So it could be, and this was our conclusion, sintered snow or ice, or just like fern, perhaps. Here is, this is sort of the calculation from the housekeeping data, but we also have some data from the calibration. And with the calibration, we penetrated into defined, into solids of defined strength. And you see at the power level 4, we'd be able to penetrate into 5 to 6 megapascal, and power setting 3, we would get into about 2 megapascals. And we're not certain about the full power level 4 efficiency that we reach that. We take this as the lower bound. So take this as a conservative lower bound to the compressive strength of the surface of the comet. Some caveats here. We had to deploy into the blind. That was not planned because we were in front of this wall or whatever it is, and could not image the surface around it, had to deploy at a shorter distance than initially planned, and therefore we did not see what situation actually that hammer was in, and there of course the maybe scoot over, and so there is to be some caveat on that, and we still need some analysis to do there. We would, of course, appreciate a Shiva image to see whether the pen stands upright. It could still be standing in some soil maybe or dust, but most likely it fell over once we retracted the deployment device. Now turning to the thermal mapper and the thermal measurements. So the thermal mapper measured during descent and the involuntary flight across the surface. Its data is being used, and has been mentioned before, to reconstruct the flight path and the attitude of the lander, and we hope that we can contribute to finding it. So this is just a short, cut out of the descent phase here. Then there is a data gap because of the anchor firing mode, and here you see that was a touchdown. Here you see how the measurement fluctuated in temperature reading as we flew across the surface, and then you see that here something changed. This is when we hit at the crater rim, and another event here, and then finally we had this touchdown, and we're sitting on this surface. We can use actually these data, if we to thermally map the surface, and we work with the infrared sensors on the orbiter to try to thermally map the pathway that we had across the surface. Now here's another time window of it when we, this is what I showed before, but here is after we landed, and you can see that we have the comet day. I mean, this thing here, this peak here, this peak here, this is when, and this is exploded here, this is when the light fell onto the spot where the thermal mapper is looking to, and we plan to use, this curve here to determine the thermal inertia of the surface. Another piece of data that we have is the temperature on the thermal sensors of the penetrator. This is how they are arranged on the nail, so to speak. And you see, this is temperatures we recorded on the balcony before we were deployed, and this is after deployment and put on the surface. And you see that there are characteristic cooling curves here, but the last two sensors cool differently, significantly differently than the others. And we tentatively interpret this cooling as we possibly went into dust, into the dust layer, and if that is so, then from the distance of that on the penetrator, we would put a upper bound on the thickness of that layer, because we don't know about the orientation of the pen exactly, of 10 to 15 centimeters. Okay, and we see the same behavior of these sensors here at a later phase. This is delta T on the measurements. So conclusions and outlook, the hardware functioned well actually, considering the complexity and the operation plan, the difficult circumstances. We find a hard surface. I think that is the most important finding, at least to date. And that this surface might be covered by a dust mantle of up to about 10 to 15 centimeter thickness. That would be much more porous and fluffy and whatever. We will use the thermal mapper data to reconstruct the flight path and estimate the thermal inertia of the final landing site using the thermal mapper and the PEN data. Qualitatively, the data so far suggests that the surface has a low thermal inertia comparative to what Miro and in particular Virtus have already concluded. Let me just add that a hard ice layer underneath a porous dust mantle was actually the result of some comet simulation experiments that we did in the 90s, although what we got at the time was not as hard as we encountered it here. Thank you very much.
Okay, the paper is open for questions. Yes, could you step to the microphone, please?
Your thermal data suggests a fluffy layer of 10 or 15 centimeters thickness, and yet that's not, you don't really see anything that looks like that in the Shiva images. Do you have a way of reconciling those two?
Not yet.
Is there another question? One more?
So if Philae reawakens in March or so, Tillman, will you be able to try again to hammer further into the layer?
What we actually want to do is then do a thermal conductivity measurement with the pen, even if it lies on the surface. And if we're really into a dust layer, we should see that in the thermal conductivity measurement clearly. And then we could confirm whether it is there.
Great.
So I have a question, which is I've heard it characterized that we hit something that was hard as a rock. So in my kitchen, I have a granite countertop. That's what I think of as hard as a rock. So is it more like a creme brulee? Is that, how would you characterize the hardness?
I would have to, I would have to, measure the hardness of creme brulee. And I don't dare to, but I mean, I imagine, old, sintered snow is, I think, what is in that ballpark. Not your granite tabletop.
Yeah.
I mean, that is definitely
so hard
harder.
As a rock is really not.
No. And I never said that. I said many stupid things,
yes,
but I never said that.
You never said it. But I have heard it characterized as hard as a rock, and I think that's not quite